Good time of day. I want to show you how I made a switch to replace my old light switch. It works remotely and connects to a Raspberry Pi. It has 3 buttons and the case is designed by my wife. Let's start on paper. I wanted to run on ATTiny 85. It's a very versatile processor with 5 GPIOs and it can run on a battery, which I actually want to use. The RF part will be the 433 MHz. Now the power to the transmitter shouldn't come directly from the battery. In the standby mode it consumes quite a significant amount of energy, so I will be switching it on and off for transmission, which means that I will use a GPIO pin of ATTiny for it. I will call it transmit enable or transmit. We also need to connect the data pin to another GPIO. This leaves 3 pins free, so we will have 3 buttons total. We cannot use multiplex in here, so 3 is a maximum. We also need a receiver which will, receive the radio frequency from the transmitter. It will connect to the Raspberry Pi. We need the ground connection, the power connection and the data connection. Raspberry Pi will run custom software which listens to the events from the GPIO. It will transmit it to the MQTT, which will in turn transmit it to the OpenHAB, which will talk to the actual payload, which is the Xiaomi LED lamps which I have. This is a topic for a different video. I will not be talking about Raspberry Pi side. So let's gather the required components. And there's a sneak peek into the future. Here is a ready product. Let's talk money. So the ATTiny costs about $1. The transmitter also about $1. The battery is 20 cents, which equates to something that is less than $5 total. This even includes the plastic for the 3D printer and the buttons. Okay, let's have a look at the code for the ATTiny. It starts with the defines for the pins we will be using. I'm using the RC switch library and here is the setup for it. This is the interrupt setup part. First we enable the interrupt for PCIn0 and then we specify the pins on which we want it to trigger. This value says that when a level changes on any of the pins 1, 2 and 3, the interrupt should happen. This is what happens when the button is pressed. First we enable the transmitter, then we do the transmission itself and disable the transmitter. In the interrupt handling routine we are not doing anything. The only thing we want from the interrupt is for the processor to wake up. Wake up from the sleep it enters here. This means that this line will actually be executed only when the CPU wakes up via an interrupt. Finally, this is the loop function which says go to sleep and when you wake up check which button is currently pressed and transmit the code accordingly. To flash the ATTiny I will be using Arduino Uno as an ISP or an in-system programmer. We need to connect them via SPI for that. And that means these pins: reset, master out slave in, master in slave out and the clock connection. Let's connect them on a breadboard, not forgetting about the ground. There. Now let's connect power. To use Arduino as an ISP we need to flash it as one. So we open examples Arduino ISP and flash it to the Arduino Uno board. Selecting the board. The COM port is selected and the programmer should be the default one. Let's upload. Now Arduino is an ISP, so we can flash the ATTiny. Here is the code for ATTiny and let's upload it. We need to select the right board, which in this case is ATTiny. The right board variant, which is ATTiny 85. Selecting the clock speed is actually optional because we are not burning the bootloader, but doing it for a good measure. The COM port is already correct. And the programmer should be Arduino as ISP. Let's flash the ATTiny. Oh look, it failed! That's because nothing works without power, so let's connect VCC of ATTiny to 5 volts of Arduino. Let's try to upload again. This time it worked. Continuing assembly on the breadboard. Removed power for safety and removing the programming wires because we don't need them anymore. Now let's connect the transmitter. Ground goes to ground. The power goes to the transmit enable pin, which we chose to be pin 4 of ATTiny or pin 3 of the chip. The data pin is pin 0 of ATTiny or pin 5 of the chip. Right, now everything's connected, let's connect power. So now it's powered and should be working. Not very exciting. In fact, I'm not even sure if it's working at all. Oh, I know what to do. Say hello to Limas DR. This is a really cool device which lets you do lots of stuff with radio frequencies. What we need now is to look at the spectrum at 433 MHz, which is the frequency of the transmitter. Let's simulate a button press. Oh look, we have a transmission. Let's try to press a different button. It should actually generate a different sequence, but we will not be able to see it. Oh, it also worked. Now I want to measure how much current it consumes. By the way, the rainbow pattern on my meter is because of the polarizer filter on my camera. I'm powering it from a lab bench power supply at 3 volts, which is the voltage of the coin cell battery I'm planning to use. So the meter is connected and let's simulate a button press. So it consumed 8 mA while transmitting, but now the chip went to sleep and the meter shows 0, which means that the current is too low to be measured. Let's go to the schematic and see what we can do. Let's remove the battery for the time being and replace it with the lab bench power supply set at 3 volts. If we now route the power line through a resistor, we could measure the voltage across it and figure out the current. Let's add the voltmeter here. I'm using a 100K resistor. That means that the voltage reading will be 100,000 times the current. Now the problem is during the startup the chip requires a significant amount of current which cannot pass through 100K resistor. So what we can do is just temporarily short the resistor. We'll let the chip power on, and once it does and goes to sleep we will remove this wire and measure the voltage. Let's do it. Resistor. The shorting wire for the time of the startup. These are the measuring wires. And finally the power line. So now it's powered on and the current is going through this wire. Let's remove it and force the current through the resistor. So the voltage is around 14 millivolts. And if we switch into millivolts measurement, we can see it's actually closer to 15 millivolts. Let's do some math. So if the voltage is 15 millivolts, the current is around 15 microamp. Yeah, my meter cannot measure such low currents. Now let's convert it into the lifespan of the battery. So the capacity is around 200 milliamp hours, which gives us around 100 years of lifespan. I think that's quite acceptable. Okay, it's working, it should work for quite a while, so let's actually solder it. The transmitter has an inconvenient connector, so I'm removing it. The desoldering iron is very handy here. The buttons I salvaged from an old printer's PCB. One of the ways to help the environment. Now onto the battery holder. This was one of the hardest parts of the project. This is the second design I've tried and I really like it. The fit is very snug and I never had problems with the contact. This is 3D printed from a Thingiverse design. I will leave a link in the description. Creative Commons for the win. Now let's continue soldering. If you're interested, the soldering footage is sped up 10 times. Mostly assembled and inserted the battery. Let's see if the power reaches ATTiny. And it does. So let's simulate the button presses. I'm using a pair of tweezers and carefully touch it. And you probably can see that the light switched on and off. This is the first successful end-to-end test. Let's try with a button for the even more end-to-end test. On and off. I've 3D printed this case for the switch. Is that how the glasses look like? Ah, there, print the new ones. Finally, the buttons go into these small depressions, just like that. Let's see if everything fits in the case. The buttons actually work pretty well. The electronics also fits pretty nicely. It's time to do the final assembly. I will be using some hot glue to secure everything in place. The buttons are in place. Before connecting the electronics, we need to remove the battery. You don't really want to connect anything which is powered. Actually, before connecting we need some vodka. To be precise, we need to wash the PCB, because we were using flux and also there can be some dirt. I like to use the ultrasonic bath filled with vodka, but multiple solvents can work here. Vodka isn't completely volatile, so we need to dry the PCB. Okay, final assembly time. There isn't much to talk about, so sit back and relax while I finish the assembly. The assembly is finally complete, and I've already removed the old switch from the wall. So now let's install the new one in its place. And it's complete, and it's working. That's great! I hope you enjoyed this project and maybe learned something new. Good luck!